Good morning, everyone. Let's get today's lecture started. We had raised a few questions in the previous lecture. If the initial density matrix is Ix and you're looking at the weak scalar coupling Hamiltonian, what should be the solution? So sigma of t here is going to be given by cos pi j. Forget h bar. To
Sj I sin I.
Very good. So let's go to the next one. Sigma of 0 is Iy and the same Hamiltonian. Iy
cos pi j
t minus
2ix sz
very good.
sin pi j.
Excellent. All right, next. Now this is too easy. I'm not going to ask this anymore. In this case, it's still going to remain Iz because I think we have done this several times now. These two commute, so I'm not going to ask this again. Okay, next one. We are talking about Sx being the initial density matrix and the weak coupling Hamiltonian.
Sx cos pi j t plus 2iz sy sin pi j.
Excellent. Thank you. I hope everybody is now getting into the groove. Who wants to answer the next one? What is going to be the chemical shift evolution of Ix with respect to Sz?
Ix.
What is it?
Ix.
Nothing else? Why not? That's correct, by the way.
Ix Ix.
Not just that. If you think about it, you're trying to ask if the chemical shift Hamiltonian for S is active and you have the state prepared only in the I state, no interaction happens between each other. Okay? That's correct. That's correct. Exactly. So this is an important outcome. Remember, I wantedly gave the same set of things in these two cases. The first and the fourth case, literally the only difference came up on where you started, but the Hamiltonian remained the same. And the Hamiltonian remained the same. You realize that the evolution happens for the I spin and the S spin, provided they are transverse. Okay, so if for instance, if this density matrix had a plus Sz, you realize that the plus Sz would just come back here because it will not evolve with this. On the other hand, if you have an Ix plus Xx plus Sx, I'm not saying Ix Sx, saying Ix plus Sx, then each of them would evolve with the scalar coupling. We'll see examples of this as we go forward. Okay, what do I mean by an evolution? Okay, next is a tricky one.
Nothing.
Okay, great. Can you tell me why so?
Commutator is 0 and it's double quantum.
Okay, how is the commutator 0? If I take a look at this commutator, we all know that it should not go to 0 directly. So I want you to take me stepwise to show this commutator as 0. Your answer is right, but let's take stepwise. At the first look of it, you realize that x to z is not 0. It should give you some form of Iy. X to z should give you some form of Sy. But interestingly, it goes to 0. Okay, that's actually the correct answer. Let's go stepwise. You're going to have, let's say, 4ix sx iz sz minus 4iz sz ix sx. So what is allowed here? What can we do as one more step?
I did some another formula AB comma CD equal to expected.
Okay, what is it? AB comma CD equal to?
A comma C. Side of
you should read it out as B commutator AC times D. Okay, then?
C.
Okay, you have to say A times B comma C times D. Okay, so this is one relationship that one could use. And what he's trying to do is therefore take the commutator of A, C with a B and D. But I tend to take an easier solution out. What? Sorry?
Matrix multiplication also.
Okay, that's correct, matrix. But I'm not showing you the matrix for the two spin-half couple system. Right? What I would do here, the first step I would do is to move the operators based on the I versus S. They commute with each other. This is now very clear to everybody. And if you guys might remember, this is one of the initial matrices I made you guys multiply. You remember that Ix times Iy will be I by 2 Iz. Right? So similar, of course, there will be a minus sign here because we are trying to do the opposite. So therefore, the 4 will remain. This will be minus because Z and X are not cyclic. So I by 2 times IY. Similarly, minus I by 2 times SY. Minus 4 times plus I by 2 by IY plus I by 2 by SY plus I square IY SY minus 4 plus I square IY SY, no, by 4. So this will be minus IY SY, while minus of minus will become plus. So therefore, you see that this commutator goes to 0. We'll try to understand the physical meaning of why this happens in a moment. So what does the math help you? Math help you to go towards the answer without understanding what that answer means. When you did this commutator, you're not thinking about physically what's going on. When we try to look at a coherence, we try to say how the bunching up happens. We still had a physical intuition. So the reason why both are given in tandem is to make sure you definitely get to the answer and start thinking about what the answer means. Many times as we go forward from here on, since the math is easy because you guys have started doing it so comfortably, you would realize that we'll do the math first without having any physical intuition, get to the final solution, and then think about what does the final solution mean. Okay, so we'll see that in one moment. I'll come back to this after we finish the solutions for the remaining ones. So let's go to the 7th one.
Sx of
Sx of?
it's only Sx.
So only Sx. Very good. Okay, this does not make much sense as a Hamiltonian. We will never be able to generate a omega is Sx if I remember correctly, but just given us an exercise. Okay, next one.
2ix sz cos pi jt plus iy sin pi jt.
Plus iy sin pi jt. Good. Last one.
2ix sg cos t into omega I.
Sorry?
T omega I.
Like this?
Yes. Plus 2iy sg sin omega t.
Omega it. Okay, remember you have to say which omega because there are two omegas that are there. There's omega s. So this is capital omega. I would rather say it as 2ix sz cos capital omega I times t plus 2iy sz sin capital I omega times t. Okay, excellent. I think the dose from last class worked heavily on everybody. I'm happy that you guys went and tried solving it. We will see how we can answer this without using the BCH. Okay, I'm not trying to say that's the right way of doing it. The BCH gives you a proper way of going towards it. Remember, we ended up starting with what is a density matrix. So let me revise what we did in the last few lectures. This is just a recap. You guys don't have to make a note of it. We said that the wave function can be represented as a superposition of the stationary states present for a given nuclear spin. And we also importantly mentioned that the time coefficients end up deciding what happens to the wave function because we are working with stationary states. Correct? So this is where we started. And after that, we were able to rewrite the time-dependent Schrodinger's equation into the Liouville von Neumann equation, which looks like this, involving a commutator of the density matrix itself with a Hamiltonian that is being worked with. Most importantly, we were able to see if Hamiltonian is time independent, then the solution of this is rather straightforward, which will be given as product of the propagators given by e power minus iht times the initial density matrix times e power plus iht. And this was once again expanded with the Bickel-Campbell-Hausdorff formula, which yet again involves the commutator between the Hamiltonian and the density matrix, which determines the evolution. Except for the most of the cases, it's a very direct commutator relationship that helps you find out. For instance, you try to ask what is the commutator between Ix and 2Ix Sz. So let's ask that. So we are trying to ask what is 2Iz Sx, the Hamiltonian, the density matrix, is the primary question. And immediately what you are able to understand, it's I times 2Iy Sz. So that's what ends up coming here. Okay, and with the sine part of it. The first one comes up with the cos component. The second one comes with the sine component. So similarly, let's take this one where you're having its IY as the density matrix to IZSZ, comma IY. This will end up being, what will this end up being? Minus I to IXSZ. Why did the minus come? Because Y and the Z are in opposite acyclic order. And of course, the I just indicates that these two are orthogonal to one another. So that will come up with the sign part of it, right? So similarly, you can keep on doing this. This was straightforward. Similarly, when you end up taking this, this is no different from whatever you did for IX, just that instead of having IX with 2IZSZ, you have SX with 2IZSZ. So I'm not going to write the same thing again. This was yet again straightforward because things commute. The only problem came when you couldn't understand this commutator. We'll just come to that again. But if you take a look at these two operators as well, let's try to see what is the commutator you're looking at. You're looking at 2IXSZ, 2IZSZ. From last class, you guys would have now been confident to say that 4 times SZ square or 4 times IZ square will be 1. This we have seen repeatedly. So I'm not going to take the 4 out and SZ square out. Your commutator just reduces itself to IX, IZ, which will be minus, what's happening here? Did I make a mistake? Minus IY should come up, but maybe I'm doing something wrong. Yeah, the mistake comes up because I ended up taking the sigma times the Hamiltonian. I should have taken the Hamiltonian times sigma. Okay, it's just the opposite. You should always take the Hamiltonian times sigma, which will be IZ, IY. Sorry, IZ, IX, which is IIY. So you did get it correctly, including the sign. Okay, so I think the textbook kind of gives a formula that will involve I power something with the E, I, J, K and all that. I leave it to you guys to go figure it out and do it. That's one way of doing it. I don't believe in formulas. You can still look at it in terms of rotation. Just that if you might remember, I gave some examples in the last class in terms of how each of this could be visualized as a rotation. This is a simple way of looking at IX, IY, IZ, but at the same time, when you're starting to have a lot more dimensions, you would also be able to go to a subspace where all these things end up happening. So I hope people are quite comfortable if a given density matrix, with a given density matrix and a Hamiltonian, you'll know how the evolution happens.
So,
yes.
So ninth question, I basically wrote it down wrong. I wrote IXSX. So in case it is IXSX, the density matrix.
In case it is IXSX, let's write it.
Both of them will...
Wait. Let me first get the question right. IXSX. And what is the Hamiltonian?
Chemical shift for IC and SC.
A chemical shift for INS.
Yeah.
Okay, very good. So you want to give the answer for that? Why don't we give 2 minutes to everybody so that they try to answer? I thought I actually gave something like that. Maybe when I spoke, I said 2IXSX, but I wrote 2IXSZ. Yeah, it's...
What Jeet said.
That's correct. That's actually correct. Maybe I made a mistake while I wrote. Okay, guys. So this is the question I intended to ask and probably asked a simpler question. The question that Shreyas wants us to answer right now is that if you have a 2IXSX type multiple quantum coherence, how does that evolve with chemical shift? We're slowly going from math to English. Good point. I think I said 2IXSX and I wrote 2IX. These things happen.
It has 4 terms.
Go ahead.
2IXSX cos omega IT cos omega ST.
Wait. Omega IT and plus omega ST.
Into
Wait. You said omega IT, omega ST. Is it a plus or a multiplication or what is it?
multiplication, sir. Cos omega IT into cos omega ST.
Okay.
2 different cost terms.
Yeah, that's what I
2
thought.
cos terms will be there.
Multiplied by. Okay. Then
Plus 2IY sin SX sin omega IT into cos omega ST.
okay.
Plus 2IY SY sin omega ST into cos omega IT. Plus 2IY SY sin omega IT sin omega ST.
What is the third operator term that you got? Maybe I wrote.
IYSY.
And the fourth one is also IYSY. Okay. Something is amiss.
Yeah.
Then in the second term that you got should be IYSY. Is that right?
The third term should be IYSX.
Yeah. IYSX. What is the second term?
So basically, it's second term is IYSX.
Right?
Yeah. And the third term is IYSX and the fourth term is IYSY.
Okay, good. So you get something as complete. And the sign costs are right? No, I think this is, he said it's sign.
It's both sides.
Yeah, he said it's sign. I wrote it wrong. Okay, good. So now the question is, what is that we understand from this? Right? Is that right?
If we write it in two separate brackets, it's a little easier to understand.
Yeah, go ahead. What is that you want to say?
2 into Ix cos omega it.
What is it?
2 into
Okay.
Ix cos omega it plus Iy sin omega it.
Okay. Times Sx.
But like, yeah, okay. Sx cos omega st plus Sy sin omega st.
I actually write whatever has been written here. So let's go with this part. Okay. The important aspect that one has to understand, let's go back to something simpler and come to this. What do we mean by go back to something simpler? Where is a simple chemical shift evolution? We have a chemical, we did it long back. So let me go to simple chemical shift evolution. This is still scalar coupling. Yeah. Something of this sort. If you might remember, this is kind of a 90-degree pulse experiment that we did. We started from IZ, then we applied a 90-degree pulse or alpha degree pulse along Y, and you ended up getting something. And if you end up applying a full 90-degree pulse, the omega-1 tau p goes to 90, and you only have Ix. So basically, you've generated the Ix state, and what happens after that was the question. At that time, when you turned off the pulse, the only thing that exists is chemical shift evolution. Correct? So therefore, what you end up getting here is that you get Ix with cos omega it. Now, the reason why we spent so much time developing the density matrix formalism is that immediately you are able to realize you get the cos part from this and you get the sine part also from this. If you are able to do a complex Fourier transformation, remember Ix and Iy, you're just trying to say they are orthogonal to one another. In some ways, you can think about this as cos omega it plus I sine omega it. Correct? So it by itself becomes exp I omega it. Of course, here I used small omega. This could as well be a capital omega for chemical shift evolution. So what you are able to realize with a simple density matrix formalism, a one pulse experiment, you can read out the outcome of the experiment just looking at the density matrix. Are you guys able to do that? So let me write what I'm trying to say stepwise. We'll come to this in a moment. So the question here is that we did a 90-degree pulse experiment. Let's assume that here is where the initial density matrix was. And then at the end of the 90-degree pulse is the final density matrix. And you let time t to evolve in which you have the density matrix after time evolution, right? So what is going to be sigma of t for a single spin system? It's going to be Iz. After you apply a 90-degree Y phase pulse, this will end up becoming Ix. You can generate whatever you want to generate. You can generate Iy minus Ix minus Iy. Ix is easy, so I ended up doing. And if only the scalar coupling Hamiltonian exists in the time t, what is going to happen? Cos of omega it plus Iy sine of omega it. Correct? And what did we keep on saying as a measurable in an experiment? You want to get the expectation value. And how is that going to come up? Trace of the density matrix, the operator itself. Okay, so let's say that we are trying to measure along the x phase. It'll be Ix. So therefore, what do we want to do? If you want to get the expectation value of Ix, it's going to be trace of Ix, sigma times Ix. So it's going to be cos omega it times Ix square plus sine omega it times Ix Iy. Is that correct? We all know for a fact, anything that is not the like term is going to go to zero. That matrix does not go to zero. The trace of the matrix goes to zero. Correct? And the trace of this is going to be 1/4 times E times 2/2. which we know is non-zero trace. So the only term that ends up remaining for Ix measurement from a 1D NMR experiment is cos omega it. If you repeat the same exercise with Iy, you will immediately realize you get sine omega it. And I said we don't end up caring about X and Y phase. We end up measuring something like M plus, which we can have an I plus equivalent, which will nicely come up to be e power I omega t. Did you guys follow what we did? We just ended up applying the density matrix formalism for a simple one pulse NMR experiment. You started from equilibrium, where we said the equilibrium density matrix is just proportional to omega I times Iz. We left the omega I out because it's just a proportionality constant. It will not change throughout whatever you do. And when you ended up applying the 90-degree pulse, the density matrix changed to Ix. The moment it changed to Ix, the next thing is that you're asking what happens in the evolution. You could have scalar coupling that exists. We will complicate that one step at a time. Let's just assume chemical shift exists. Let's assume that it's a water molecule that you're studying with NMR, which only has one proton and no coupling associated with it. Correct? So at that point, you have determined the density matrix. And what did we promise if you learned density matrix formalism? You'd be able to predict the outcome of the experiment. And how is the outcome of the experiment predicted? Take the operator that you want to measure, take the product of the operator with the density matrix and ask what is the trace. Anything that has a zero trace, you cannot see. Anything that has a non-zero trace, you can see. This was the premise in which we set up. So we ended up taking the density matrix at that position and then try to take what is the expectation value of, let's say, I plus, you'll end up getting e power I omega t. So now the important aspect is this is your time domain signal. If you end up Fourier transforming this, complex Fourier transforming, you will get a peak at plus omega I and nothing at minus omega I. Do you guys see that? So what we are able to do is to start from something really simple in a representation, which is the initial density matrix, and try immediately understand how the spectrum will look just by doing two steps really fast. Did you guys feel that? Correct. So you guys have been enabled to do some calculations much faster than looking at, okay, how will it change? No. You're able to go there quickly. The only thing that's missing here is relaxation. So the major assumption that we do is that whenever we are looking at how pulses and delays work, we don't incorporate relaxation into this formalism. So for all practical purposes, we will not be showing peaks as proper Lorentzians. We are just going to show them as delta functions. Okay, now you can ask yourself another question. Yeah, let's say I have an IS spin system where the initial density matrix is given as Iz plus Se. Let's assume that both are proton so that the gamma is same. Correct? Go back and do the same formalism with a 90-degree pulse applied to both. Then what you will end up getting is something like Ix cos omega it plus Iy sine omega it plus Sx cos omega it, so omega st, plus Sy sine omega st. Correct? Therefore, you'll be able to realize without any scalar coupling, let's say JIS is 0, yet again, it gives you a picture that you'll get two resonances, one at plus omega I, another at plus omega S, and nothing at the because you're doing quadrature detection. Remember the cos, how does the cos go with Fourier transformation? How does the sine go with Fourier transformation? If you use both, you'll only get the real part of it. Make sense? So slowly you're able to realize if you construct the density matrix, I can actually visualize the spectrum. True? You're getting the power. So my only request to you guys today is to go back, repeat the same process where the Hamiltonian during the second part is not just omega I Iz plus omega S Sz, but also has a pi j is to Iz Sz term. Immediately, whatever we learned for the AX spin system, solution will come already. You guys remember we did the AX spin system after the semi-classical picture? That answer will come right away. So everything that we have developed in semi-classical picture and quantum picture are one and the same. But the quantum picture will be able to take you to the solution much faster. For instance, the classic example is what Shreyas now raised. Now let's go back to where we started. Now I will only talk about what is observable and what does it mean. And how do we talk about this? Oh, you get a e power I omega t term. That means you get a resonance at omega, capital omega. You see how quickly we go to the spectrum? So you're able to see how when you just look at the density matrix, you'll say what is the answer to that entire thing, right? So it's the same thing we are going to do right now for the multiple quantum coherence terms. Slowly, I'm changing the math and operators into English words. So please follow how I change it, because this is how questions are going to come. I won't ask you an exam, how does 2AX SX change with chemicals? I mean, with omega IZ plus omega IZ. That's not the way I'll ask. The question, the way I'll phrase it will be like, how does a multiple quantum coherence term evolve with chemical shift of the involved spins? This is how I'll write it in English. Ix can be written as I plus I minus by 2. Same for S plus S minus by 2. If you end up taking a look at what are the terms that are there, you will have I plus I plus S minus I minus S plus I minus S minus. These are the four terms that will be involved. And if you pay close attention, this is a double quantum coherence because it's I plus S plus, so is I minus S minus. While the middle ones are I plus S minus and I minus S plus, which are zero quantum coherence. Anything that's not first order, it will be called as multiple quantum coherence. This is actually a mixture of double quantum and zero quantum coherences. Why is this question a very important question to ask at this moment? Is because I promised you guys that the semi-classical picture will give you no intuition of this, but the quantum picture would. So I'm happy that you raised this question. So let's go back to asking what is it we are trying to achieve. We are trying to ask, okay, we have seen how does a single quantum coherence evolve with scalar coupling. So that's the way of telling it in English. Did you guys see that? How does a single quantum term evolve with scalar coupling? Weak coupling. Similarly here, single quantum coherence with weak scalar coupling. This is something called longitudinal order. This is more like how does a polarization evolve with scalar coupling? So if I ask you, does polarization evolve with scalar coupling? What will be your answer? Yes or no? Okay, maybe the definition of evolution is unclear. Evolution means after something happens as a function of time, the time should be a part of the answer. For instance, you started with Ix and you're able to realize that a t term started to creep in. So that's called evolution. It starts to become as a function of that part. But if you end up taking the Iz term, you realize that you still got the Iz and there is no t power dependence. So that implies polarization does not evolve with weak scalar coupling. Polarization as Iz is polarization. Population difference is polarization. Iz comes up as a polarization. I'm just giving English terms for all these operators because when people speak, they won't say, oh, Iz is present. No, they say, okay, when you put it in equilibrium, you generate a polarization. So immediately I want the operator Iz to come to your head.
So we don't call it polarization where it is Ix.
Ix is coherence. Single quantum coherence. Why single quantum? Because Ix is I plus I minus by 2. So let's take something like this. 2IXSZ. It is still a single quantum coherence because Ix is I plus I minus, but the S is more like polarization. We will see some spectral aspects of it as we go forward. This will be called as an antiphase single quantum coherence. Why is it called antiphase? The SZ pulls out whether the S spin is an alpha or beta. So if it's an alpha, it'll be plus. If the S spin is an beta, it'll be minus. Okay, we'll see some aspects of this as we go forward. Please remind me if I forget it. Okay, but let's go back to the main question that was raised, meaning that if you have a multiple quantum coherence, how does it evolve with a chemical shift? I hope the last 10 minutes have given you a perspective on how the operators will be termed in English. This problem was given to make you guys think. For instance, this problem was a crucial problem, as I said, because what you are able to realize, multiple quantum coherence does not evolve with weak scalar coupling. That's the outcome of this. Let me write it so that you guys are comfortable. MQC doesn't evolve with weak scalar coupling Hamiltonian. Why am I spending so much time telling this? Is that soon, when we go to pulse programs, where NMR course will take complete access towards, that's what we are going to see. We develop density matrix formalism. When we look at the experiments from the NMR perspective, I'll be making such statements and going faster. So when I make such statement, this should come back in your head. Similar to the fact that when I made that Ix times Iz is I minus I by 2 Iy, this came to your head because I made it earlier. So we are going to compound. This should come into place, this should come into place, and therefore this should come into place, and therefore you will understand the experiment that we are trying to understand. Make sense? So it's really layered understanding and comprehension and using it at the right time that you want. So what was the outcome of learning this is that you realized multiple quantum coherence does not evolve with scalar coupling. True? Similarly, the question here is, okay, the multiple quantum coherence does not evolve with scalar coupling, but does the multiple quantum coherence term evolve with chemical shift? Nice question. Yeah. Before we came here, we learned single quantum evolves with chemical shift, single quantum evolves with weak scalar coupling. Now we are asking, does multiple quantum, which does not evolve with scalar coupling, does it evolve with chemical shifts? We are slowly able to go to the fact that if you see the first term itself, I'll be able to say where the answer comes up. I don't have to see all the two terms that are present. We just see the first part of the term. How many of you are able to appreciate this is nothing but cos of omega I plus omega s times t plus cos of omega I minus omega s times t. Of course, there's a 1/2 for overall. Cos of A, cos B is 1/2 cos A minus B plus cos A plus B. Something of that sort, right? Do you guys see that that's the same manifestation that comes? So the interesting thing that happens is that while a single quantum coherence, in-phase coherence, evolves with the chemical shift of that given spin, a multiple quantum coherence evolves with the sum and the difference of the precession frequencies. This is a little too difficult to understand, but all I'm trying to say, let's say that you're doing a proton experiment at 500 megahertz, where you end up picking the offset with respect to 500 megahertz as the chemical shift. Correct? We define chemical shift as omega of the compound when omega naught times 10 power 6. This is how we define chemical shift. So if you get omega I, capital omega I, you know what is delta of I. So therefore, we are quickly slicing everything off. We said, okay, we have an equilibrium density matrix. Then we reduce the equilibrium density matrix. Then we ask, how does it evolve for all the different operations I do? And therefore, if I get some final thing, I'll be able to visualize the spectrum. That's the long and short of it. Yeah. So now for a single quantum coherence, well, the evolution happens with that level of order of coherence, which is single quantum. For a multiple quantum coherence, it happens as a sum and difference. You can think about this as double quantum and a zero quantum. Right? So this is a very important question. Interestingly, by direct acquisition, NMR also cannot see this. We'll understand why later. Okay, just take it from me as a fact right now. Although you're able to realize that chemical shift will evolve with as a sum and difference. So basically what will happen, let's say we are looking at a carbon and proton NMR. Can we imagine that? Yeah. So proton, let's say, resonates at 400 megahertz. And therefore carbon will resonate at? Why? Because the gamma is 1/4. Correct. So therefore, anything of the sort of omega I plus omega s will be resonating at 500 megahertz, while omega I minus omega s will resonate at 300 megahertz. Remember, you are only on resonance at 400 or 100. Therefore, you cannot see either 500 or 300. So you still cannot directly measure it. Spectrum, no, it will not. There's something called selection rules. This will be forbidden as a selection rule. But don't lose your hopes. You can still measure it indirectly from NMR. Okay, we will go to that after the mid-sem. Okay, but this is more than enough for now in terms of understanding. I still did not give you the physical picture of what's happening. So we'll take a look at that right now. So,
Sir,
yes.
so like our frequencies that change, right? Because of that. So plus 100 and minus 100.
Yeah.
But then we can see chemical shifts. That's also changed, right?
That's also a change, but I did not give you the entirety of how the hardware works. The hardware goes to the normal perception frequency of that channel and looks only very close by. It cannot see broadband. So it goes to 400 megahertz and looks within a few kilohertz. It cannot do 400 megahertz plus minus 100 megahertz. It cannot do that.
Very tiny.
That's exactly correct. Your chemical shifts are so tiny. So we want to go to the megahertz and look within the kilohertz within that spread. So what were we saying? We said that your density matrix at some point is multiple quantum. And then we said if the Hamiltonian is chemical shift Hamiltonian for both the spins, what is the final term? And the final term that we got was Ix Sx cos omega it plus cos omega st. Then we said it evolves as a sum and difference of chemical shifts. I'm assuming omega I is greater than omega s here. Otherwise, the sign will just flip. Okay. At the same time, the homework questions that you guys did was sigma 0 being 2 Ix Sx, and then the Hamiltonian being 2 Iz Sz with a pi j, whatever, with a pi j. Correct? And what did we say? That just remind whatever it was. Why did this happen is the question. Can we try to answer this? Mathematically, we said scalar coupling will not evolve, but chemical shift will evolve as a sum and difference. So why does that happen? All this stems back to the states that were present. So if you guys might go back and see the energies of this will be something like omega I by 2 plus omega s by 2 plus pi j by 2. Yeah. So this will be omega I by 2 minus omega s by 2 minus pi j by 2. Omega I by 2, sorry, minus omega I by 2 plus omega s by 2 minus pi j by 2. Minus omega I by 2 minus omega s by 2 plus pi j by 2. Now, when you're talking about the multiple quantum transitions, you're talking about the exchange between alpha, alpha, beta, beta, or alpha, beta to beta, alpha. When we are talking about 2i plus s plus or I minus s minus, you're trying to talk about transitions that happen between alpha, alpha, and alpha, beta. And when you're talking about transitions that happen between these two, you're talking about 2i plus s minus or I minus s plus. Carefully pay attention. If you take the energy differences between them, omega I by 2 plus omega s by 2 minus of minus omega I 2 plus minus omega s by 2 will automatically come omega I plus omega s. You guys see that? We just take the energy differences between these two. That happens because the plus pi j by 2 cancels by itself. Scalar coupling is there, but the net effect is not there. But the chemical shift will evolve with the sum of both. Make sense? But on the other hand, if you see the flip-flop happening between alpha beta and beta alpha, if you take the difference between them, you will get omega I minus omega s. Here, yet again, the pi j will get cancelled because both of them are minus pi j by 2. The only reason why you end up getting single quantum coherences is because the signs of this pi j are opposite, and therefore you will get evolution with scalar coupling as well. Yeah. I'm very happy that we went through this. Yet again, I did not even touch 5 minutes of what I wanted to teach today. But I think this served as purpose to understand why we want to see density matrices, how it gives you the answer. After you give it gives an answer, you can go back and look, okay, what's happening and what does it mean, right? Remember, math is a tool to understand what comes out, at least in this course. And the math is at times very easier than looking at things this way. Correct? Okay. Since I have only about 5 to 7 minutes left, what I would like to do in the last few minutes is to make you guys understand how to write matrices for this 2 spin half systems. That's all I have the time for today. Let's ask ourselves a question here. What is the question? What is the dimension of density matrix for IS spin system, which we saw a few classes back? It's a 4x4 matrix. It depends on the number of states that are there. There are 4 states, alpha, 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 beta, beta, alpha, and beta, beta. Therefore, it's a 4x4 matrix. But if you guys go back, we were very happily writing multiplication of the density matrix with an operator where the density matrix, you know, for this case is 4x4, but you've only seen a representation of IX matrix as a 2x2. Mathematically, this is stupid. You cannot do this. because you should have the dimensions match so that the multiplication can be made facile. And remember, a trace of a matrix only kind of can be defined for a square matrix. Okay, let's say that even this is like a 4x2 and 2x2 or whatever, you'll get a 4x2 where the trace doesn't make sense, right? So you need a diagonal matrix. So you realize that this has to up itself to a 4x4, correct? So now what I'm going to do is to make you guys understand how you can write a 4x4 representation of the spin matrices for a coupled spin system. So let's say we take an IS spin system. Remember, when we wrote alpha alpha, we meant that the first spin is an alpha, second spin is an alpha. When we wrote alpha beta, we meant that the I spin is an alpha and the S spin is in beta. So for almost all part of this course, I'm going to write I first followed by S. Okay. So now how do we expand dimensions? Before expanding dimensions, let's write some important things. So I square is 3/4 E2/2. IZ is 1/2 100 minus 1. IX is 1/2 0110. IY is I/2 01 minus 10. Is that right? Or did I swap the minus one? Go check it out. But overall, what you are able to see, these are the representations for the I spin, all these matrices. Similarly, you can write for the S spin also. And remember, you'll write it exactly the same as the I spin because both are spin half. The Pauli's matrices in the eigenbasis of Z do not change for spin half. Okay. Yes. So now we will see how does this 2x2 matrix expand to a 4x4. This is done by something called a direct product. What's a direct product? Let me give an example. Let's say you have A matrix and a B matrix, where A matrix is given as a 2x2. And a B matrix is given also by a 2x2. Then what is the solution is what we are trying to see. Generally, if you do a matrix multiplication, you multiply it in a certain way where you once again get a 2x2 back. But here you're doing a direct product, or some people call it an inner product, where the dimensions increase. Okay, so what is going to happen? This is going to be, literally take this one and multiply all parts of this. So A11, B11, A11, B12, A11, B21, A11, B22. And then take the second element, multiply every aspect and put it on the other side. A12, B11, A12, B12, A12, B21, A12, B22. Similarly, take this one and multiply the entire thing and put it up here. That's going to be A21, B11, A21, B12, A21, B21, A21, B22. Then the last one will be multiply the whole thing and put it up here. So it's going to be A22, B11, A22, B12, A22, B21, A22, B22. Okay. So here what happens when you have a 2x2 and a 2x2, you do a piecewise multiplication of rows to rows and columns to columns to get a 4x4. This is a general definition for direct product. If you have a m by n, direct product p by q, the dimensionality will be mp by nq. It doesn't have to be square at all. We deal with square matrices, so I defined it for a square matrix. Okay. What I request you to do for the next class, or at least as a weekend homework, which I'll be giving, for a IS spin system, let's define how many operators are there. Okay. We just defined E in the basis of I, IZ, IX, IY. Let me just write it in order. IX, IY, IZ. Correct? This forms a complete set for the spin I. True? Similarly, ES, SX, SY, SZ forms a complete set for the S spin system. Now what we have to do is to take each one of them and do a direct product. How many operators come then? You have 4 operators here, you have 4 operators. We have to take every operator and expand the dimensions, how many operators come up? 16 operators come up, correct? So the first operator of this is EI direct product ES, where you write the I matrix first, which will be 1001, direct product 1001, which is also the identity of the S spin. If you go back and do this, you're going to only get I in the diagonal elements, which becomes a E4 by 4. Okay, go back and do this to convince yourself. I'll just give one more example. Let's say you want to do the IZ operator. IZ operator will come when you take a product of IZ with identity of S. So that's going to be 1 over 2, 100 minus 1, direct product 1001. So what will happen here? 1 over 2. Yeah, 1 times the entire thing. So what is that going to be? 100 minus 1. Sorry, 1001. And then you have a 0 times everything as 0. So I'm going to just write 0000. Similarly, this will also be 0000. And the last part will be minus 100 minus 1. Okay. You realize how the IZ matrix became 4 by 4. Similarly, I'll write SZ matrix. SZ matrix will have EI product SZ. Always keep I first and S followed by S. Don't change the order, in which case the matrix representations will be all over the place. Okay, did that make sense? Yeah, so this is going to be, go back and do this, 1000, 0 minus 100, 0010, 000 minus 1. So you see that the minus 1 comes here, and on the other hand, it alternates here. So go back, do the direct product for all the 16 operators. What are the 16 operators? EIS, IX, IY, IZ, SX, SY, SZ, 2 IX, SX, 2 IX, SY, 2 IX, SZ, 2 IY, SX, 2 IY, SY, 2 IY, SZ, 2 IZ, SX, 2 IZ, SY, and 2 IZ, SZ. Okay. This is going to be quite a bit of a task, but if you guys do it, you'll be convinced on how these matrices come, and look at the traces for all of them. For all of them, all the matrices will give 0 trace. But when you start taking products, they'll start to behave differently, which we will see next class on why it matters. Okay. In some ways, I ended up covering some part of the 1D NMR experiment, which is supposed to be next week, this week itself, because we ended up discussing quite a bit of it today.